Welcome everybody to part 2 of the lectures on dynamic soil properties. In the part 1 lecture that was uploaded to YouTube a few days ago, the topic of that lecture was how do we measure dynamic soil properties, and we talked about using in situ field methods, mostly geophysical methods that involve measuring the shear wave velocity of the soil, and also laboratory methods, both low strain and high strain methods. In today's lecture, we're going to talk a little bit about the properties of dynamic soils themselves and the behavior of soil when you begin to strain it. So let's introduce the idea of the shear modulus behavior of soil. So if we get in and we test soil, let's pull up the whiteboard here. And let me create some axes that we'll use for this little discussion. Let's flip this around 90 degrees. Perfect. Okay. So let's say that this is shear stress and this is shear strain. And let's get a red line here, and it's going to demonstrate what happens. Now, if I start loading up soil, start straining it, it's going to load, and eventually it might even start to yield a little plastically. Now, if I unload it, the soil is going to come down, and it's not going to follow the same path that it did going up, because soil is not elastic. Soil behaves in a plastic manner. And if I were to follow this down this way and load it to the basically the same level, well, let's see, that would be tau, and of course this would be, sigma 1, tau 1. If we load it to the same strain, we could see that the soil would kind of follow this type of banana type loop. And then if we loaded another cycle, it might look something like this. Loaded another cycle, it might look something like this. So what we end up getting is kind of this permanent deformation of the soil with strain. And it's weakening every time we go through another cycle. Okay? So if we continue that process, if what we were to do then were to plot the path of these peaks, they would look something like that, right? And the path of these peaks would look something like this. So that blue line is something that we're interested in, and we're going to call that blue line the backbone curve. If we come and look at just one cycle of that cyclic loading, we're going to look at two definitions of shear modulus. The first one is what we're going to call the secant modulus. The secant modulus is the if we were to just draw a straight line to the stopping point of our cycle from a strain of 0. So think of it as just like the average shear modulus for that particular cycle. So if this cycle came all the way over here on another iteration like that, if that's the case, then the secant modulus for that cycle would look something like that. And that angle, that G, would equal the secant modulus for that cycle. So that's the secant modulus essentially follows the backbone curve that we defined before. Or maybe I should say the backbone curve defines the secant modulus. And the secant modulus represents the average shear modulus of the soil as a function of cyclic strain. Now let's contrast that with what we call G max. the maximum shear modulus. This is the shear modulus of the soil at its initial state, and when the soil is still behaving elastically. And so it represents the steepest slope and represents the most elastic point of the soil. No other point of the soil is going to be, or I should say, no other point of the backbone curve is going to have a steeper slope than that associated with G max. And again, just remember that G max represents then the elastic behavior of the soil at very, very low strains. And you'll recall this figure looks familiar. Remember how we said that the ratio of these areas, the area beneath the secant modulus curve represents the idealized energy from a single cycle, and also the energy here in gray, which represents the energy lost by the soil through friction and particle interaction. And the ratio of those two gives us the, well, that doesn't look very good. Let's try this again. The damping ratio. I'm not very good at drawing those Greek letters, unfortunately. Okay, now if we were to perform a series of high quality shear tests, so let's say like this would be like resonant column testing. So say we have a high quality sample, it's as undisturbed as possible, we bring it into the lab, we're going to perform a series of strains on the soil, and we're going to measure its corresponding stiffness, our shear modulus G, okay? And let's plot the secant modulus of the soil versus the log of the shear strain that we apply to the soil. What we'd see is the following behavior. Obviously at very, very low strains, when the soil is still in its elastic behavior zone, we'd see some pretty high shear moduli. And so we would say then, okay, that high shear modulus corresponds to the elastic modulus, elastic shear modulus, so we'll call that G max. But if we were to continue to apply more cyclic strain to the soil, what we'd see is that with higher strain, the secant modulus of the soil goes down and down and down and down and down until eventually we get really low values of secant modulus at high strains, which means we've really fundamentally damaged the soil, and it's become just a fraction of the stiffness that it was before. So the trend that we tend to see is, and this is important, that the stiffness of the soil as defined by the shear modulus decreases as our cyclic strain increases. So the more we strain our soil, the higher the amplitude of the strain, the less stiff our soil becomes. So one convenient way that we can do this would, or that we can represent these curves, is if we normalize the secant modulus by the maximum shear modulus. So if we normalize it, then what we can say is, instead of saying G max, we just have a value of 1.0, and everything is relative to a value of 1. So these curves then have a special name. We call them modulus reduction curves, and we use these curves when we want to predict what the stiffness degradation behavior of the soil is with cyclic shear strain. So we can use those modulus reduction curves to estimate values of the secant modulus, but in order to do that, we have to come up with estimates of the maximum shear modulus. So we can use that, the ratio G over G max. Without G max, those ratios are meaningless. So there's a couple of ways that we can do this. Obviously, the best way to obtain G max is going to be through low strain filled or laboratory tests with undisturbed soil samples. And the reason is low strain means that the soil is still in its elastic region, and G max is an elastic property of the soil. Therefore, if I'm doing a low strain test, then I can just basically measure G max directly. Now, we don't measure modulus per se, but what we do measure is shear wave velocity of the soil. So if I can measure that through any of the tests that we've talked about, like seismic reflection, seismic refraction, MASW, SASW testing, cross hole, up hole, down hole, any of those tests that measure shear wave velocity, if I get those estimates, then I can compute Gmax directly. But what happens if we aren't measuring shear wave velocity? Then we need to rely on other methods. A popular method in consulting today is to use various correlations to estimate the maximum shear modulus. But always keep in mind that this approach is never as good as measuring the shear wave velocity directly. But it's better than just pulling a number out of a table or just guessing some conservative number for the soil. So a popular equation that comes out of the Kramer textbook is shown right here. And this is from a large series of laboratory tests that were performed on a wide variety of soils. And so you can see basically this equation is a function of the void ratio, of the over-consolidation ratio of the soil. K is a function of OCR as well. Atmospheric pressure, which is known or given. The mean principal effective stress. I think we'll talk about that in a second. And then a stress exponent, which we usually assume to be equal to 0.5. So here's the equation. Here's that generic equation for void ratio. So if we can measure or approximate the void ratio in the soil, then we compute that function f of E using this equation right here. Or we can use an easier function using this Jamilkowski equation. But both should give you pretty similar results. If we need to get K, that's also it's a function of void ratio, to be honest, but people have correlated it to the plasticity index from the Atterberg, computed from the Atterberg limits. So remember, plasticity index is simply equal to the liquid limit minus the plastic limit of the soil in water contents. And so this is an easy way to come up with estimates for your K value. Now, what is the mean effective stress? Well, the mean effective stress is basically trying to account for the fact that the soil is three-dimensional, and you have stresses acting on all sides or all faces of the soil. And so we're trying to account for all of those stresses. Now, normally when we compute effective stresses, we're only talking about the vertical effective stresses. The mean effective stress is trying to account for the fact that you've got stresses acting on all sides of your little soil element. Or I should say a soil cube right now. So really what it is it's, we can compute the mean using this equation right here, where sigma 1 is the maximum, usually the vertical stress, sigma 2 is the intermediate stress, and sigma 3 is usually the minor stress. Now, if we're assuming that sigma 2 and sigma 3 are equal, meaning that we don't have like a plane strain condition, then we can write the equation this way, where you'll recall that K naught is equal to the horizontal stress divided by the vertical stress. And K naught is the at-rest earth pressure, lateral earth pressure coefficient. And sometimes, that lateral earth pressure coefficient for a lot of soils is approximately equal to 0.5 or so. And if that's the case, then you can approximate it with this equation right here. But of all these equations, my favorite is this guy right here that I'm circling. That one just makes the most sense. There's lots of relationships out there that we can estimate this K0 term, and it's usually a function of the friction angle of the soil. So just grab a hold of your favorite one of those equations and you can compute the mean effective stress. Okay, now if I have sand soils, I don't need to use that big previous equation. We can use something that may be a little easier. Seed and Idris came up with an empirical equation based on their laboratory testing, and it's this function right here. This K2 max is just a coefficient, and it's a function of either void ratio or relative density, whichever one we prefer. And so whatever your soil is, just grab the corresponding value from this table, and this mean effective stress is computed just like we discussed in the previous slide. Now, if you have fine-grained soils, then we're going to use correlations that are based on the undrained shear strength. That's S sub U, or sometimes it's also C sub U, just depending on the terminology that you're using. So these are ratios of maximum shear modulus divided by undrained shear strength, and it's a function of the OCR of the soil, and it's a function of the plasticity index of the soil. So you can go ahead and interpolate, or you should interpolate between these table or these tabulated values, and they'll give you a good estimate of this ratio. Once you get this ratio, multiply it by the undrained shear strength, and you should be go. You're going to be using consistent units, of course, between the undrained shear strength and the shear modulus. And then you can refer to table 6-6 in the Kramer text for many other relationships to estimate the maximum shear modulus. And these are all functions of standard penetration test, cone penetration test, dilatometer, or pressure meter. They have lots of different relationships. Not all of these relationships are actually reported in table 6-6, but their references are, and so you can go into the literature and find them. You just have to be careful, though, because remember, this Kramer textbook was published in 1996. He's currently working with Professor John Stewart to come out with the second edition of this textbook, but it's probably still at least a year or two out from the time I'm recording this lecture. So some of these relationships included in this table 6-6 are probably outdated. But they're still good. I mean, the data that they're based upon is still valid, and so don't necessarily shy away from them, but I would just say do a literature search and compare them with more modern or updated equations. I want to emphasize the importance, though, of using these correlation equations that we've been talking about the last few slides very, very cautiously. You have to understand that when we have these in situ tests like SPT, CPT, etc., unless it's a seismic CPT where we're actually measuring shear wave velocity, we are using high strain field methods to correlate a low strain dynamic soil property. So there's going to be a lot of variability, a lot of scatter in these relationships. So just be aware of that and understand that these aren't perfect predictive relationships. Now let's talk a little bit about the general behavior of modulus reduction curves. There are a lot of different factors that affect the behavior and the general shape of these modulus reduction curves. The two most significant factors by far are the soil's plasticity, such as the plasticity index, and the soil's effective stress. So let's focus first on the plasticity of the soil and how it impacts modulus reduction. So I just drew a generalized sketch here of a series of modulus reduction curves, again a function of shear strain, and corresponding G over G max, where you got to remember that G is the secant shear modulus of the soil from the backbone curve. Now if I take just a given value of shear strain, I may get this value of G over G max if I have a really low plasticity index. Conversely, I may get this value of G over G max if I have a really high plasticity index. So the trend that we see is that increasing the plasticity index for a given strain is going to increase my G over G max ratio. It's going to cause my modulus reduction curves to shift to the right and up. Now let's look at the effect of effective stress. We can do the same type of thing if for a given shear strain. If I have a low effective stress, I'm going to get a lower G over G max value than if I have a higher confining effective stress. So the higher the confinement, the less stiffness I lose, basically. The less the confinement, the easier it is for the soil to lose its stiffness with a given strain. Therefore, increasing the effective stress is going to increase my G over G max behavior. But, this is a big but, this effect of effective stress becomes less pronounced with increasing soil plasticity. So if I have a really high PI value in my soil, I'm not going to see a big differentiation in the curves based on my confining stress. But if I have a low plasticity in the soil, I would definitely see more of an effect from confinement. Okay, so let's look at the effect of effective stress on modulus reduction. If I have PI of equals 0, or if I have non-plastic soil, generally what we see is this behavior of these kind of gradually sloping curves, and they're going to be impacted then by our effective stress, like we talked about, pretty significantly. You know, if I come up at a given strain, you can see that that range of G over G max, depending on my effective stress, is pretty significant. If I have a high plasticity and I come up at a given strain, you can see that there still is an effect, but the difference between G over G max for those same stresses is not as great as they were, as the effect was over here. That's all I'm saying, is that plasticity tends to, I guess, negate this effect from confining stress to some degree. So here's a table out of the Kramer textbook, and it's actually taken from a famous or a classic source on soil dynamics, Professor Ricardo Dobry and his colleague Vucetich from RPI in New York. Very famous researchers that are experts in soil dynamics. They demonstrated or produced this summary of factors and how they impact G over G max. So you can see things like geologic age, cementation of the soil, cyclic strain, PI, over-consolidation ratio, all those things, and you can see how G over G max is impacted by these factors. I recommend that you be very familiar with this table and understand how each of these different factors could impact the behavior of the modulus reduction curves. So before we get to damping behavior, let's again review. Modulus reduction curves are intended to give us, for a given, say, strain value, modulus reduction curves are supposed to give us what this secant, let's see, let me draw corresponding axes here. So there's gamma again. So if we take that same strain value, and this is G over G max, where again G represents secant modulus. So if the slope of that line is, say, G1, then what that basically means is for this point, that's going to be equal to, you know, G1 over G max. And then for maybe this value of strain, this slope here may be equal to G2. That slope's going to be G2 over G max. And the point of these curves then is that it's going to give us this shape, or the function that we can use to predict the backbone curve for this particular soil. That's the whole point of modulus reduction curves. Okay. Modulus reduction curves always are presented in tandem with damping behavior, or we'll introduce the idea of damping curves. Now, we've introduced the idea again of the damping ratio right here in the previous lecture, or a previous lecture. But again, the damping ratio is a function of this ratio, where we take the area of the energy dissipated by one cycle of loading in our soil by the theoretical energy, maximum energy from one direction of loading, and it's basically the area underneath the secant modulus, the secant modulus strain curve. So the ratio of those two areas multiplied by 1 over 4 pi is what gives us the damping ratio. So if we were to plot, then do the same thing we did before with modulus reduction curves, but this time for every cycle, or every cycle of cyclic strain, we computed that ratio and calculated the damping ratio. What we would see is behavior that looks like this, and we call this behavior the damping curve. So as strain increases, the soil loses its stiffness, becomes damaged, and as the soil fabric and structure becomes damaged, the damping of the soil increases. So you can see with increasing strain, the damping of the soil also increases, and it becomes more efficient at burning energy with every cycle. So just like modulus reduction curves, damping curves have been developed for numerous types of soils. You should always consider modulus reduction curves and damping curves together. Think of them like being married, or they're in pairs. You can't have a modulus reduction curve without a damping curve. So like on this axis with cyclic shear strain, I have modulus reduction here. But on the same plot, just on a different axis, I could have damping ratio shown here. And so for every modulus reduction curve for a particular soil type, I should have a corresponding damping curve. If we look at the behavior of damping curves, they pretty much follow the same rules as modulus reduction curves, only opposite. So for instance, if I look at plasticity index for a given cyclic shear strain, if I have a low plasticity soil, I'm going to have a high damping ratio. But if I have a high plasticity soil, I'm going to have a low damping ratio. Therefore, increasing plasticity index decreases my damping ratio. So you can see this table here. Be familiar with this table as well and be able to compare and contrast this behavior of the damping ratio with the listed behaviors of the modulus reduction curves. So I mentioned that there have been several different relationships that have been developed and published for many soil types for modulus reduction curves and damping curves. Several of these equations are listed here. You can see they go all the way back into the 80s. Personally, in my consulting, because I did a lot of work in California, and particularly for Caltrans, the California Department of Transportation, we used this model, the GeoIndex model by Roblee and Chiou, developed in 2004. We used it a lot. And it was developed by these guys specifically for Caltrans on use in Caltrans projects. It was developed for soil, not rock, which is a benefit. If I go back to this slide, a lot of these relationships were developed principally for rock to be used in site response analysis. But this relationship of the GeoIndex model was developed specifically for soil. And the way it's going to work is we're going to divide up the soil into three basic categories. Category 1, or PCA, are basically primarily coarse grained soil. So these are sands, gravels, even coarse silts, I would almost say, if it behaves like a sand. Category 2, FML, is going to be fine-grained, low plasticity soil. So fine-grained matrix, low plasticity. Here are the Atterberg limit properties and the fines content properties that define whether or not a soil should be in Category 2. Category 3 is going to be a fine-grained, high plasticity matrix soil. So we're going to have more than 30% passing, again, the number 200 sieve, and we're going to have a plasticity index greater than 15% in the soil. It's important to note the limitations of this model. It is not applicable for rock. It's not applicable for thick deposits of gravel or very high plasticity soils, plasticity index greater than 50. Highly over-consolidated soil, where you have an over-consolidation ratio greater than 4, and highly organic soils. So make sure that you're not applying this model to any of those types. Here's how the GeoIndex model works. The G over G max, or modulus reduction curve, is given by this equation right here, where we have a reference strain, and we have a coefficient that are given to us based on our category, whether it's PCA, FML, or FMH, categories 1, 2, or 3. This is the strain value that goes into our modulus reduction curve, and this is the corresponding G over G max. The damping curves are similar, though we have a minimum damping value. We have this, that's min damping, I believe. And then we have this coefficient that comes from the testing or the data. And then we have this macing damping coefficient. And what this macing damping coefficient is, we'll talk a little bit more about macing damping, but macing criteria are a set of rules that govern the loading and unloading behavior of soil. And so it defines, like, if I load up on my stress strain curve, the macing rules are going to tell me what the stress strain behavior is when I begin to unload. And I know I'm not going to come straight back down the loading line because the soil is not elastic. This Mason criteria are some rules that will define what it's going to look like when I begin to load it, and if I go back and try to reload it again. So here's our function for the demacing right here. These C1, C2, C3 are just coefficients that you compute. And they look nasty, but they're not really. And remember again, this alpha is a coefficient that is given to us based on our category of the GeoIndex model. And then let's see, this demacing alpha at 1% is, we compute it down in this equation down here, and we can plug it into this demacing equation up in here. One thing to bear in mind, all right, is you want to make sure that we're using the proper units, I guess, for strain, whether it's in percent or decimal strain. I'm going to pause the presentation actually because I want to make sure that I can tell you whether to use percent or decimal value of strain. So bear with me for just 1 second. Okay, I'm back. Thanks for your patience. So I'm glad I looked that up. This gamma here, you got to remember that it's gamma in percent. It's a percent strain, okay? This reference gamma is exactly as it comes in the table itself. So yeah, don't get confused on this. Remember that we're dealing with percent strain with just gamma, but gamma ref is just the decimal value straight out of the table. So this is what I'm talking about. So this is the recommended coefficients for the GeoIndex model. This reference strain right there, okay, that is gamma ref. Don't convert that to percentage. Just put that number in exactly as it's written in this table, okay? But the gamma that you use is going to be a percent of strain. There's your alpha, your D-man, and of course your beta. All right. For category 2, there's your reference strain, alpha, beta, reference strain, alpha, beta. So you just plug those values in, and notice, by the way, that it's also a function of depth or confine. Really what that is it's a proxy for confining stress, as we talked about before. So this is why I really like this model, because it accounts for the plasticity of the soil through the different categories, whether it's category 1, 2, or 3, but it also accounts for the confinement in the soil by the appropriate depths shown here on the left. So last thing I want to discuss with you here, being able to accurately model the changes in the soil dynamics property with strain is a big deal. It's a really big deal. It's critical if we want to predict behavior and actual displacements and strains and stresses in the soil when it's hit by cyclic loading and the soil begins to strain back and forth. Now, the ability, or I should say the actual predicting of a soil strain based on an applied stress, or just the stress-strain relationship in a soil, is what we call the soil's constitutive model. So a constitutive model of a soil would be a model that would allow us to predict how it's going to strain within the given applied stress. Now, developing what I call a universal, accurate constitutive model for a wide range of soils or all different soil types is kind of the holy grail of geotechnical engineering, and more specifically geotechnical earthquake engineering. And the reason it's so hard is because of pore pressure effects. As you start to strain soil back and forth, the pore pressure inside the soil does wacky things. And if the pore pressure does wacky things, then the confinement or the effective stress in the soil does wacky things too. And so you can get the soil beginning to gain stiffness as you strain it, and that's called dilation. And then it can suddenly lose stiffness as pore pressure goes up again. And so pore pressure goes up, then your soil loses stiffness. Pore pressure goes down, your soil dilates, gains stiffness. And in multiple cycles of loading, the soil can go through numerous cycles of dilation and softening, dilation and softening. And so it's a very complex and difficult problem to try to model. And there are numerous researchers and engineers who have spent a lifetime and continue to do so to try to better model the constitutive behavior of soil. When we start talking about non-linear site response analysis, constitutive models are the key to accomplishing that. And a key in the development of constitutive models is our ability to model modulus reduction behavior and the corresponding damping behavior of soil. So I hope that this lecture was helpful to you, and feel free to shoot me an email or send me a message if you have any questions that are concerning you or bugging you, or feel free to just approach my TA or approach me when I get back from traveling. But in the meantime, thank you so much, guys, for your attention, and have a wonderful day.